Good afternoon, Professor Aldini. This is a reliability analysis of Boo's Toy Company, presented December 9th. Our group members are David Cormier, myself, Jeffrey Ray, and John Schulte. Our project overview, we're going to give you a project scope and background, a FEMA analysis, present the raw manufacturing data collected from the manufacturing line, some reliability models with our fault tree, and reliability block diagram, present some statistical analysis from Minitab, and follow up with conclusions and suggested improvements. To give you an overview, scope of the project, we are working on the Boo's Toy Company production line. The scope of this project is to identify potential defects within the manufacturing process and suggest implementation of different procedures in order to reduce defects produced by the system. Manufacturing process overview is a toy car assembly line with a steel press station, a grinding station, a weigh station, a panning station, and finally a visual inspection station before shipping. Here's our FEMA analysis. The three primary sources of defects are dimensional inconsistencies, improper surface finish, and improper coating applied to the product. Here we have our FEMA analysis with our detection, occurrence, severity, and other modes of rating each of these failures. The most significant failure of defect producing activity that we noticed from the manufacturing line is the grinding stage, which has an RPN or risk priority number of 648. That means that is the primary focus of correcting this manufacturing line. Here is a sample of some raw manufacturing data received from the company. I was only able to fit 20 batches on the screen, but we received a total of 35 batch samples from the production line. Next is our fault tree. We have our line, press, grinder, and painter stations. The press station can stop the manufacturing line, or the grinder or painter station could also stop the line. We have a reliability block diagram. Since the product goes from station to station, there's no parallel processes going on. Therefore, we use the series reliability calculation in order to calculate the total reliability of our system, which we calculated to be 94.4%. Each of the defects received by the weigh station and the visual inspection station are where the defects are kicked out. Those reliabilities are respectively 96.2% for the machine and 98.2% for the visual inspection, and we also have a defects part per million opportunity of 30,857.
So these charts here, which are C charts, show the defects detected by the machinery and the defects detected by the human inspector. And so you can see that there is one batch in each set of data that has one outlying point, and we are looking to remove that outlying point from this process. Here is the overall defects for all the detections with our C chart, showing the defects per batch. This is the modified C charts after our processes had been implemented, which we'll talk about after in the next few slides. This is the total defects detected in the process after modifications. And typically, a range of 20 to 30% is acceptable for a toy line in terms of scrap rate. And so starting with a 94.4% survival rate, by increasing or by implementing preventative maintenance, we were able to reduce the scrap rate from 94.4% to 96.9%, which improves from 3 sigma levels to just beyond 3 sigma, close to 4 sigma levels. So we started with 30,857 defects per million, and we reduced that to about half. Also, the reduction of cost due to the scrap rate was reduced from 28 to 19%. So once again, in conclusion, we're suggesting preventative maintenance to replace the grinding bit and the painting tip at the start of each shift instead of during the shifts to reduce downtime during normal work hours. So Thank you for listening to our presentation.